vivo. É isso aí. Estamos ao vivo.
Tá certo. Então, boa tarde a todos e a todas. Tá. Temos aí 5 minutos de atraso. O Ramesh aí, que é indiano, não foi pontualidade britânica, né, Ramesh? Mas, enfim, vamos dar início, então, à palestra do professor Ramesh. Tá? Então, o professor Ramesh aí, ele é doutor em Química Orgânica Sintética pelo Indian Institute of Chemical Technology, em 2014. Atualmente é professor visitante do Programa de Pós-Graduação em Química Tecnológica e Ambiental, da FURG. Sua pesquisa é voltada para o desenvolvimento de novas metodologias sintéticas, empregando catálise com metais de transição, especialmente através de reações de acoplamento cruzado de carbono-enxofre, carbono-carbono, carbono-nitrogênio, via catálise heterogênea. Ele também trabalha com síntese de novos compostos bioativos, comumente empregados na indústria farmacêutica. Então, professor Ramesh, aí, com você, aí, você tem o tempo que achar necessário para apresentar aí o seu trabalho, apresentar a sua palestra aí. De antemão, já gostaria de agradecer a todos que estão assistindo. Qualquer dúvida pode ser colocada aí no chat do YouTube e a gente esclarece aí e pergunta diretamente para o professor Ramesh. Então, é com você aí, professor.
Tá, obrigado, professor Marcelo. Boa tarde a todos. Good afternoon, everyone, again. As Professor Marcelo explained about me, my name is Ramesh Katla. I'm a visiting professor at EQA FURG. Today, the topic of the lecture is Introduction and Applications of ß-Cyclodestrin in Organic Synthesis. So, in this lecture, I am going to divide two parts. Part one is especially introduction about ß-Cyclodextrin. Here, I am going to show you structures, shapes, and other properties of ß-Cyclodextrin. And part two is applications of ß-Cyclodextrin in organic synthesis. Okay. This lecture has been divided into the following categories. First one is introduction, results and discussion, experimental procedure, conclusion, and acknowledgements. Let's start with the introduction of ß-Cyclodextrin. What is ß-Cyclodextrin and what sizes and shapes it has? So the ß-Cyclodextrin, generally, I'm going to talk about the general introduction about cyclodextrins. Cyclodextrins are torus-shaped cyclic oligosaccharides possessing hydrophobic cavities, which bind substrates selectively and catalyze chemical reactions with a high selectivity. And also, cyclodextrins catalyze the reactions by supramolecular catalysis involving reversible formation of host-guest complexes by non-covalent bonding as seen in enzymes. Then we can see what is the supramolecular chemistry. For example, according to Professor Jean-Marie Lev, defined in his Nobel lecture as supramolecule is the beyond the molecule. Supramolecular chemistry denotes the chemistry beyond the molecule involving non-covalent intermolecular forces between two or more species. So non-covalent interactions may be electrostatic interactions or hydrogen bonding or van der Waals forces, etc. And here I'm going to show you structures of cyclodextrins. Cyclodextrins are cyclic oligosaccharides with hydrophobic cavities. And cyclodextrins are torus-shaped cyclic oligosaccharides consisting mainly of alpha-cyclodextrin has 6 D-glucose units, beta-cyclodextrin has 7 glucopyranose units, and 8 gamma-cyclodextrin has 8 D-glucose units. linked by alpha 1,4 glycosidic linkages. Let's see the structures of cyclodextrins. This is the structure of alpha cyclodextrin, which contains 6 glucopyranose units. We can see 1 glucose units are linked 1 and 4th position of another glucopyranose units. This alpha CD has 6 glucopyranose units. This is the structure of beta cyclodextrin, which contains 7 glucopyranose units. These we are giving numbering from this carbon 1, 2, 3, 4, 5, 6. So the linkages, this is the glucopyranose linkages 1, 4 linkage with another glucopyranose units. And the last cyclodextrin is gamma cyclodextrin, which has 8 glucopyranose units, linkage of 1, 4 glycosidic linkage with another. Here, among all these cyclodextrins, this gamma cyclodextrin is more soluble in water because it has more hydroxy free groups. And compared to alpha cyclodextrin is more strained molecule compared to beta CD and gamma CD. Though the solubility of alpha CD is more than the beta CD because of the strained molecule. This beta cyclodextrin is soluble at room temperature, a little bit soluble in water. These are the structures of cyclodextrins. And here I am going to show you the basic unit of glucopyranose unit of beta cyclodextrin. Here in glucopyranose units, we are starting numbering from this carbon. It has 1, 2, 3, 4, 5, 6. Here, this is the general structure of beta cyclodextrin. The previous slide I showed you a chair form of beta cyclodextrin. Here I am showing you the general structure of beta cyclodextrin. This is now I am going to show you history of cyclodextrins. So generally cyclodextrins are also called cycloamyloses or cyclomalto-oligosaccharides. Until 1938, there was no correct structure for cyclodextrins. The first Fredenberg, who characterized them as cyclic structures composed of alpha 1,4 linked glucose units. After this publication, it took several years to before the molecular weights of the cyclodextrins were determined. This cyclodextrin chemistry has been started in 28th century. Here we can see the sources of cyclodextrins, how cyclodextrins are produced. Here, generally cyclodextrins are produced from starch by the action of the enzyme cyclodextrin glucosyl transferase CGT, and alpha cyclodextrin is produced from cyclohexaamylose, and beta cyclodextrin is produced from cycloheptaamylose, and gamma cyclodextrin is produced from cyclooctaamylose. Now these are the shapes of cyclodextrins, and previous I showed you some slide structures of beta cyclodextrins. Here the shapes of cyclodextrins. This is the shape of alpha cyclodextrin, and this is the shape of beta cyclodextrin, and this one the shape of gamma cyclodextrin. Here you can see these tub we are using at our home. These shapes looks like tub shape. So here there is a cavity. This small circle indicates cavity, hydrophobic cavity. This is a larger cavity, and this surrounded. I can show you in this picture. This surrounding region is hydrophilic region. Only this circle, this cavity shows hydrophobic region. Here, the top side edge, right side and left side, this top part region, secondary hydroxyl groups are located top of the beta cyclodextrin. In the bottom and smaller area, this region, primary hydroxyl groups are located. Here, This is the hydrophobic cavity of the cyclodextrins. This is interior because it is located inside the beta cyclodextrin. This is outer, exterior surface of the cavity, right? In this part, here, this part, all the hydrogens, primary hydroxy groups are located in this position. But in this cavity, only secondary hydroxyl, here, secondary hydroxyl groups are located. Primary hydroxyl groups are located outside the beta cyclodextrin, and secondary hydroxyl groups are located inside the beta cyclodextrin. This is hydrophobic cavity where it attracts organic molecules. This around this beta cyclodextrin, this is hydrophilic cavity where the water molecule attracts in this region. Here, this is the cavities. We can see the diameter of cavities. In alpha cyclodextrin, the interior surface of the cavity is 5.7 angstroms and exterior cavity of the surface 13.7 angstroms. In beta cyclodextrin, interior surface of the cavity is 7.8 angstroms. Exterior cavity is 15.7 angstroms. It is depend upon the glucopyranose units. In beta cyclodextrin has 7. Because of this, it has a little bit of large cavity than the alpha. Here, in gamma cyclodextrin, the interior surface of the cavity is 9.5 angstroms. And the exterior cavity is 16.9 angstroms because it has gamma CD has 8 glucopyranose units. So it has a little bit the size of the cavity is more than the alpha and beta. These are the shapes of cyclodextrin. This is the here schematic representation of hydrophobic and hydrophilic regions of cyclodextrin cylinder. This is, you can see, this shaded line indicates hydrophobic sites, and this indicates this indicates hydrophobic sites, and the bottom indicates hydrophilic sites. Here, this hydrophobic means it attracts only organic molecules or non-polar molecules, and this area attracts only water molecules. You can see this region is located for aqueous molecules, and this region attracts organic molecules, right? And this is also, I can show you schematic representation of hydrophobic and hydrophilic cavities in cyclodextrin structures. Here you can see this is the structure of cyclodextrin, and inside this is the hydrophobic region. It attracts organic molecules. It favors only organic molecules. It doesn't favor for aqueous molecule. This outside, this outside region, hydrophilic region, it attracts water molecule, right? This is the side view of cyclodextrins. You can see here interior, this small circle indicates interior cavity of the beta cyclodextrin. Secondary hydroxyl groups are located top side of the beta cyclodextrin, and primary hydroxyl groups are located in the bottom of the beta cyclodextrin. Because this is very important here, hydrophobic cavities, it is depend upon the cyclodextrins. So we have studied about alpha, beta, and gamma cyclodextrins. Their cavity is depend upon the cavity. The incoming substrate will come and fit here and carried out the organic reaction. That's why I'm showing you interior cavity of the beta cyclodextrin. Okay, well, and this is the another. Alpha, beta, gamma cyclodextrins are naturally occurring compounds, but this is the structure of delta cyclodextrin. So this is a very rare cyclodextrins, but this has 9 glucopyranose units are present in a delta cyclodextrin. It is obtained from the commercially available cyclodextrins by the chromatography method, and this delta cyclodextrin had greater aqueous solubility than the beta cyclodextrin and lesser than the alpha and gamma cyclodextrin. Even though this delta cyclodextrin has 9 glucopyranose units, the solubility of the water solubility of this cyclodextrin is more than the beta cyclodextrin but lesser than the alpha and gamma CD. But the larger series, because it has 7 glucopyranose units, it's considered as a larger cyclodextrin, are not regular cylinder shaped. They are collapsed structurally, and hence their real cavity is even smaller than the beta cyclodextrin. If you observed other cyclodextrins such as alpha, beta, and gamma cyclodextrins, they have special hydrophobic cavities. But in case of delta cyclodextrin, it has collapsed structurally. This structure is collapsed so that the interior surface of the cavity is lesser than the beta cyclodextrin, even though it has 9 glucopyranose units, but the structure is collapsed. Therefore, the hydrophobic cavity is lesser than the beta cyclodextrin. This is the least stable cyclodextrin among the alpha, beta, and gamma cyclodextrins. And here I am showing you schematic representation of cyclodextrin inclusion complex formation. So we can see here what is the inclusion complex and what's the mean of inclusion complex, how cyclodextrins forms inclusion complex with substrates. As you can see, this is organic molecule. It's called para-xylene. This is the substrate, and I called as guest molecule. Host molecule is beta cyclodextrin. This is a beta cyclodextrin. It acts as host molecule. These para-xylene act as guest molecule. These small circles represent as water molecules, because our catalyst, our beta cyclodextrin, or all cyclodextrins are dissolved in water, so that I took aqueous environment. So these circles represent water molecule. This is the guest molecule. This is beta cyclodextrin act as host molecule. You can see the cavity, beta cyclodextrin, the cavity, interior surface, hydrophobic cavity of beta cyclodextrin like this. I'm talking about general cyclodextrins. The cavity of the cyclodextrin has this kind of, the substrate or guest molecule can fit inside these hydrophobic cavities, because this is organic molecule. It is not dissolved in water, so that this this around this beta cyclodextrin, it attracts water, but especially in this hydrophobic region attracts organic molecules, so that this para-xylene molecule can fit inside the hydrophobic cavities of the beta cyclodextrin. Then like this, after made the inclusion complex, the molecule looks like this. Only this aromatic ring can fit inside the hydrophobic cavity of the cyclodextrins. This external part is occupied by water molecule, right? This is the CD, cyclodextrin inclusion complex with substrate with organic molecules, right? This is how we can determine the cyclodextrin inclusion complexes. There are various methods to determine the cyclodextrin inclusion complexes, such as X-ray, fluorimetric measurements, nuclear magnetic resonance spectroscopy, circular dichorism, ESR, polarography, colorimetry, diffusion across semi-permeable membranes, and surface strain measurements. Among all these analytical studies for the catalyst inclusion complexes, the good and extraordinary methods are X-ray and NMR methods have been established, important tools for the determination of inclusion complexes. And as well as H1 NMR spectroscopy provides a quick determination for the inclusion complexes of beta CD with substrates. In addition to this, in the structure of beta cyclodextrin, C3 and C5 methane protons of glucose units of the cyclodextrin point inside the hydrophobic cavity, and 2 and 4 methane protons are located outside of the beta cyclodextrin. So outside part is not observed in NMR, only inside part such as C3 and C5 protons are observed in NMR. Okay, here this is the beta CD supported other catalysts. You can see here here beta cyclodestrin supported with sulfonic acid. Then the catalyst structure is beta CD sulfonic acid. This is the beta CD sulfonic acid catalyst. Here beta CD is supported with palladium chlorine, palladium nanoparticles. You can see when we replaced beta cyclodextrin, one of the hydroxyl primary hydroxy groups to other functional groups, then it means the activity when we replaced beta cyclodestrin with other functional groups or other metal catalysts supported on beta cyclodestrin, then the catalytic efficiency will increase, so that many researchers around the world, they are going to support catalyst on beta CD to carry out reactions in organic synthesis, right? Yeah, this is the characteristics of alpha, beta, and gamma cyclodextrins. Here, you can see the important characteristics of alpha, beta, and gamma cyclodextrin. Alpha cyclodextrin has 6 glucopyranose units, beta has 7 glucose units, gamma has 8 glucose units. The molecular weights of alpha cyclodextrin is 972, beta cyclodextrin has 1135, gamma cyclodextrin has 1297. This is the cavity in water 1 gram per 100 ml at room temperature. This is the solubility of alpha CD 14.5 and beta CD 1.85 at room temperature. Gamma CD 23.2 at room temperature. And specific rotation alpha 150, beta 162.5, gamma 177.4. This is the cavity diameters, right? Interior surface of the cavities. In alpha CD 4.7 to 5.3 and beta CD 6.0 to 6.5, gamma CD 7.5 to 8.3. And this is the height of torus. The height of torus all are equal in all the CDs. Alpha, beta, gamma CDs are equal. That is 7.9 angstroms. Diameter of outer periphery in alpha 14.6, beta 13.4, gamma 17.5. This is the approximately volume of cavity in angstroms 174 in alpha, 262 in beta, 427 in gamma CD. These are the crystalline forms. All the cyclodestrins alpha, beta, gamma is crystalline white powder. Crystal water weight percent alpha 10.2, beta 13.2 to 14.5, gamma 8.13 to 17.7. This is the diffusion constant at 40 degrees temperature. Alpha 3.443 and beta 3.224 and gamma CD 3.000. Right, these are the important characteristics of alpha, beta, and gamma cyclodextrins. Right. Now, until now, I have explained about the introduction of cyclodextrins. Now, I am going to talk about the applications. Applications means I have carried out 2 methodologies using a beta cyclodextrins. We have published many methodologies using beta cyclodextrin, but in this lecture, I am going to show you 2 of my methodologies that I used beta cyclodextrin as a catalyst in my reactions. Let's see. Here, see the first advantages of the beta cyclodextrin. Beta CD is a recyclable catalyst. It is eco-friendly, environmentally benign, and green catalyst. It is non-toxic and non-hazardous. It is readily available, economically viable. It is easily handling. It is easily separate beta CD from the reaction mixture. Because of these advantages, we carried out some methodologies using beta cyclodextrin in aqueous medium. Now we are going to see methodology about N-phenyl agipins. So that I wrote here importance of N-substitute agipins. Let's see the importance of N-phenyl agipins. These are the marketed drugs which containing agipin skeleton, such as imipramine, carbamazepine, oxacarbazine. These are marketed available drugs. Not only this, in addition to this, there are several drugs containing agipin skeleton exhibited more biological activities, such as anti-malarial drug therapy, anti-HIV, stomach disorders, and anti-arrhythmic and hypertension glaucoma. This is my first methodology, which I published in 2011 after I joined as a research scholar, like a PhD student in the group of Professor Dr. YVD Nageshwar. So here, there were no reports before I published on this mighty. I first published this mighty by commercially available amines reaction with dimethyl acetylene dicarboxylate, diethyl acetylene dicarboxylates with 2,5-dimethoxy tetrahydrofuran in the presence of ß-Cyclodestrin in aqueous medium at 50 to 60 degrees temperature. Then the resulting product N-phenyl agipins were obtained in good yields in the ranging between 31 to 94%. Here, ß-Cyclodestrin is commercially available and economically viable, and H2O is green solvent. So this methodology has several advantages, like I spoke before you. That's so that I developed this methodology and published in 2011 in Tetrahedral Letters, right? And I have done optimization reaction conditions using different catalysts for N-phenyl agipins. Here, first, a model reaction was carried out using aniline 1 millimole, dimethyl acetylene dicarboxylate 1 millimole, and 2,5-dimethoxy tetrahydrofuran 1 millimole in the presence of gamma cyclodextrin in aqueous medium. Then the resulting product was obtained in 78%. Then we changed this reaction to alpha cyclodextrin as a catalyst under similar reaction conditions. Then the product yield was decreased to 38%. Then we changed catalyst alpha to ß-Cyclodestrin under similar reaction conditions. The resulting product was obtained in 92%. Then in entry 4, entry 5, we used 2-hydroxypropyl ß-Cyclodextrin and methyl ß-Cyclodextrin as catalyst on this reaction. Then the product yield was decreased to 42 in case of entry 4 and 40 in case of entry 5. Then in entry 6, we did not use any catalyst on this reaction. We used water as a solvent to carry out this reaction. Then the resulting product was obtained in 36%. Among all these catalysts, ß-Cyclodestrin was given excellent yields of the desired product. Remaining compounds we have done by using ß-Cyclodestrin, right? After we have done the optimization conditions of the catalyst, we have synthesized several N-phenyl agipins. Here you can see electron donating groups attached at para position of amine, such as methoxy, and here hydroxy, moderate electron donating group methyl, and a neutral group hydrogen, as well as electron withdrawing groups such as nitro, bromo, chloro, 3-nitro have been given excellent yields of the desired product. In case of benzyl, aliphatic amine has given 35% of yield because of the low reactivity of the aliphatic amine. And this is used dimethyl acetylene dicarboxylate. Here we use diethyl acetylene dicarboxylate. Here the same electron donating groups methoxy and hydroxy. This is moderate electron donating group methyl, and neutral hydroxy. The electron withdrawing groups chloro, bromo, nitro, 3-nitro, and these have been given excellent yields when compared to aliphatic amine. This as in case of aliphatic amine has low reactivity. All these conditions, we used amine 1 equivalent, which means 1 millimole, DMAD or DEAD 1 equivalent 1 millimole, and 2,5-dimethoxytetrahydrofuran 1 millimole, and catalyst used 10 mole percent at 60 degrees temperature for 4 to 7 hours. This is the proposed mechanism of N-phenyl H-base. Here, a beautiful mechanism with ß-Cyclodestrin for the formation of N-phenyl H-base. Here you can see the aniline. Aniline first reacted with diethyl acetylene dicarboxylate, then generates the carbene ion. This carbene ion is stabilized by primary hydroxyl groups and secondary hydroxyl group of ß-Cyclodextrin, which further react with 2,5-dimethoxytetrahydrofuran, then form the intermediate one. In this intermediate one, nitrogen has lone pair of electrons. It make the nucleophilic addition between carbonyl function, then form the cyclization product. This hydrogen electrons transfers towards the towards these two carbons, then this pi bond transfers on nitrogen. Then here in intermediate 3, the new pi bond is formed. Here the adjacent position above the nitrogen, there is a methoxy and hydrogen. This hydrogen transfers electrons towards these two carbons. Then automatically this methoxy is eliminated as methanol, MEOH. Then form the another pi bond here. After elimination of these two, then the desired product is formed. This is a beautiful mechanism with ß-Cyclodestrin. And I'm going to show you beta-CD aniline inclusion complex. First, we can see how we can form the inclusion complex. We take beta-CD 1 millimole was dissolved in 15 ml of water, then warmed up to 60 degrees temperature until it gets the clear solution. Then add the substrate, which is aniline 1 millimole, then stirred for 3 hours at 60 degrees temperature, then cool the reaction mixture to 5 degrees temperature, then keep it for 7 hours. The precipitate will filter and dried and sent for the analysis. Here you can see all these NMRs were taken in DMSO D6 300 MHz equipment. This is the Aniline Spectra, and this middle spectra is represented as ß-Cyclodextrin spectra. The bottom of the spectra is represented beta-CD inclusion complex with aniline. Here you can see after aniline sit inside the hydrophobic cavity of the ß-Cyclodestrin, the spectra has come like this. This is the evidence of ß-Cyclodestrin forms and inclusion complex with aniline. Right. Here I'm going to show you another methodology for the synthesis of benzimidazoles and benzodiazews. Here benzimidazoles and benzodiazeous motifs are very important compounds in pharmaceutical industry and medicinal chemistry. These are the drugs thioflavin T, jopelrestat, C11PLB, oxfendazole act as an anti-helminth, omeprazole act as anti-ulcer drug, and dibazole act as anti-hypertensive drug. Not only this, especially riluzole, which shows extraordinary biological activities such as anti-HIV, antioxidant, anti-inflammatory, and anti-malarial properties. And not only this riluzole, and some of them are benzodiazews containing drugs such as pimobendine and mebendazole, which have been shown excellent anti-cancer activity. And in addition to this, pimobendine is a veterinary medication and it is used as a calcium sensitizer. Now, apart from this, mebendazole is used to treat roundworm and whipworm infections too. And here we have recently published benzimidazoles and benzodiazews by commercially available orthophenylene diamines or 2-amino benzene thiol with various aromatic or heteroaromatic aldehydes in the presence of ß-Cyclodestrin in water at 60 to 65 degrees temperature. As you can observe, I used in the previous methodology 60 temperature. In this methodology, I used 60 to 65 degrees temperature because the solubility of ß-Cyclodestrin at room temperature is 1.82. As I explained in previous slide, this ß-Cyclodestrin is not soluble in water at room temperature. So that I am using 60 to 65 degrees this methodology. And the previous methodology, I used 60 degrees. At 60 degrees temperature, beta-CD is soluble in water. And this methodology, this methodology has so many advantages. For example, these are commercially available starting materials. Here, ß-Cyclodestrin is a recyclable catalyst and water is a green solvent. And this might be as very important in pharmaceutical sector. And this publication published in RSA in 2015. And here we can see the optimization of the reaction conditions for the synthesis of desired product. First, a model reaction carried out using orthophenylene diamine with salicylaldehyde in the absence of any catalyst and solvent for 10 hours. The product was obtained in trace amount. Then we used water as a solvent for 8 hours without using any catalyst. Then the product yield was obtained in trace. Then we used alpha CD 10 mole percent as catalyst in aqueous medium for 4 hours. The resulting product yield was obtained in 22%. Then we changed alpha cyclode to gamma cyclodextrin in aqueous medium. Reaction for 5 hours. We used catalyst 10 mole percent. Then the product yield was obtained in 30%. Then we changed these catalysts to ß-Cyclodestrin under aqueous conditions for 4 hours. We used catalyst 10 mole percent. Then the resulting product was obtained in 94%. In entry 6, we increased time from 4 hours to 10 hours. Then we increased catalyst mole percent, 10 mole percent to 15 mole percent. There was no effect in the yield of desired product. So finally, we concluded that ß-Cyclodestrin catalyst is efficient in aqueous medium for 4 hours for the preparation of 2-phenyl benzimidazoles, right? After we have done the optimization conditions of the reaction, then we have successfully accomplished several 2-phenyl benzimidazoles. Here, electron donating groups methoxy, methyl, moderator group methyl, hydroxy, and electron withdrawing groups attached at a para position or ortho position of benzaldehyde rings has been given extraordinary yields. Here you can see we applied this methodology to diversely substituted aldehydes. Here 3 substituted aldehyde 3-nitro, ortho substituted aldehyde 2-nitro, 4, and here 4-nitro. So all the substitutions of benzaldehydes reacted well with OPDA. Then the resulting product was obtained. In case of aliphatic aldehydes such as Crotonaldehyde and 2-phenyl propanol. The traces of the product yields were obtained because of the low reactivity of the aldehydes. Then we applied this methodology for the preparation of 2-phenyl benzodiazews in the presence of beta-CD. Here, withdrawing groups bromo, donating group hydroxy, methoxy, these are and a simple hydrogen benzaldehydes and 2-methoxy, 2-bromo, 3,4-dihydroxy and tri-substitution aldehydes has been given excellent yields, and also heterocyclic compound indole 3-carboxylaldehyde also given good yields. All the reactions we used aldehyde 1 equivalent, 2-aminothiophene or 1,2-diaminobenzene 1 equivalent, ß-Cyclodestrin 10 mole % at 60 to 65 degrees temperature in aqueous medium. And this is the proposed mechanism for the synthesis of 2-phenyl benzodiazole or 2-phenyl benzimidazoles. Here first, the simple condensation reaction takes place with benzaldehyde and orthophenylene diamine or 2-aminobenzodiazole. This first imine forms like this. Then this X equal to nitrogen or sulfur. It has a lone pair of electrons, excess electrons readily donates towards this benzylic carbon. Then this pi bond migrates towards the nitrogen, then form the 5-membered cyclic ring. Then in the presence of air oxidation, then here form the aromatic ring. The finally form the desired product. This is the plausible mechanism of the reaction. Here, I am showing you inclusion complex with beta-CD with para-hydroxy benzaldehyde. This A spectra represents beta-CD H proton NMR spectroscopy, and this B figure indicates inclusion complex of beta-CD with para-hydroxy benzaldehyde. You can see only in beta-CD only it's methane 3 protons and methane 5 protons are observed in NMR because these are located inside the hydrophobic cavity. Remaining protons are not observed because they are located outside of the beta-cyclodextrin ring. So our para-hydroxy benzaldehyde located can fit inside the hydrophobic cavity of the beta-CD. Therefore, only this C3 methane proton 3 proton and methane 5 proton observed here. After making inclusion complex, you can see the variation between figure A and figure B. After making the inclusion complex, the little bit CH3 protons and H5 protons are little bit goes towards the upfield due to the anisotropic effect. And all these spectra were taken in DMS4D6 in a 300 MHz equipment. And we have also done the recyclability of the catalyst with 2-phenyl benzodiazole. Here you can see this blue indicates product yield, and this wine color indicates catalyst recovery. The fresh catalyst, the product yield was obtained 81 with catalyst recovered 90%. In the first cycle, the product yield was obtained 80%, catalyst recovered 88%. In the second cycle, the yield was obtained 78, the catalyst recovered 84%. In the third cycle, the product yield was obtained 76% and catalyst recovered 82%. You can see the 4 cycles. There is a little bit of loss of yields with respect to the catalyst recovered. It indicates catalyst is efficient towards promoting reactions in organic chemistry. That's well. Yeah, this is the experimental procedure for the synthesis of benzimidazoles and benzodiazoles. You can see, take 50 ml of round bottom flask, then add 15 ml of water with 10 mole % of beta-cyclodextrin. Then stirred for 15 minutes. at 60 to 65 degrees temperature until it gets clear solution. Then add 1 equivalent of benzaldehyde, then 1 equivalent of another substrate added to the reaction mixture. Then stir it at 60 to 65 degrees temperature for an appropriate time. Then extract. Then the reaction mixture was cooled to room temperature. Then add ethyl acetate and water. Separate organic layers and concentrated on rotary evaporated, and purification using 30% of ethyl acetate, 70% of hexane. Then the desired product was obtained in good yields. And this is the paper that we published in 2015. And conclusion. Here we have developed an eco-friendly one-part protocol for the synthesis of 2 substituted benzodiazews and benzodiazews in good to excellent yields. These are the advantages of this methodology. Catalyst is economically viable and recyclable, and it is non-toxic and non-hazardous, and it is readily available. It is easily handling water used as a green solvent. These are the advantages of the methodology. And this is my Google Scholar score. My total citations are 1029, and H index is 20, I-10 index is 29. And this is my Web of Science publication. Total publications are 46. Total citations are 845. I have 6 book chapters published in various international journals, and I have one review article. And here my H index is 18. And this is my ResearchGate score is 31.2. This is H index 19. 17 is excluding self citations. And these are the references for this presentation. And I would like to thank to Química, Tecnológica e Ambiental and Escola de Química e Alimentos, Federal University of Rio Grande, and I would like to thank to Professor Dr. Bruno for giving me this opportunity to explore my presentation with many people over online, and also thanks to Professor Marcelo Godai and in this presentation. And I would like to thank to all the viewers who are attending this presentation. Thank you so much. If you have any doubts, ask me.
Certinho. Parabéns pela apresentação, então, professor Ramesh. Tá. Temos agora um período aberto para perguntas. Todos podem aí escrever no chat. A ideia é a gente trocar aí conhecimento, em especial com a química aí relacionada às beta-cyclodextrinas, que foi o que o professor Ramesh nos apresentou, tá? Então, é só escrever no chat, alguém tiver alguma dúvida. O professor Ramesh optou por falar em inglês, mas ele fala português muito bem, então poderia ter falado em português também, mas é sempre bom a gente, em especial o pessoal da pós aí do PPGQTA aí, se familiarizando ainda mais com a língua inglesa, que é de extrema importância para a academia, certo? Bom, enfim, até o momento não temos nenhuma pergunta, professor Ramesh. Eu tenho uma pergunta em especial, tá? Eu gostaria que você falasse um pouco com relação à solubilidade das beta-cyclodextrins, uma vez que, como você mencionou mesmo, eu acho na grande maioria dos artigos aí, inclusive dos seus trabalhos, as beta-cyclodextrinas, elas são utilizadas como catalisadores heterogêneos, eu acho que seria isso, né? Mas a gente também pode fazer modificações estruturais nessas beta-cyclodextrinas, né?
Isso.
Então, nesse sentido, quais seriam os melhores solventes para a gente fazer essas modificações estruturais?
Professor, Eu usei alfa, beta, gama, cyclodestrins. Eu não troquei functional groups. Por exemplo, eu mostrei uma beta-acid com sulfonic, ácido sulfônico. Isso dá mais eficiente, mas beta-cyclodextrin eu usei o mesmo catalisador. Meu trabalho beta-cyclodextrin como catalisador, mas ela não é solúvel quase no solventes orgânicos. Ela é solúvel só no água. Água, temperatura ambiente, ela não é solúvel, só dá de mais que 50. E entre 50 até 85 é bom temperatura para solúvel beta-cyclodextrin.
E no caso de etanol a quente, poderia ser solúvel também a cyclodextrina?
Não. Pode solúvel em DMSO e DMF, os dois. Outros, ela não é solúvel.
Ok. Então, no caso, ela poderia ser solúvel em solventes polares apróticos. No caso do DMSO e do DMF.
Sim, sim.
Okay. Porque é importante, se você vai fazer uma modificação estrutural, né? Você falou aí de uma série de vantagens na utilização das beta-cyclodextrinas, né?
Isso, aí, professor.
Você pode, daqui um pouco, modificar na estrutura, né? E até mesmo fazer um estudo aí de estrutura-atividade, daqui um pouco ver o potencial biológico ou farmacológico, que eu tenho certeza que deve ser muito explorado, né, com relação a isso.
Isso, professor, isso é verdade. Pois, outro grupo tem, onde eu fiz doutorado, outro grupo só mudar functionalities, grupos de funcional no beta-cyclodextrin. Eles publicaram jogos organic letters também, porque isso é muito eficiente. Mas tem pesquisa bastante, entendeu?
Tem bastante coisa a ser explorada.
Isso. Mas tem boa atividade, consiga bastante publicações, mais que 6 impact factor, entendeu?
Não, ótimo, excelente.
Sim.
Você publicou também, né, Ramesh, com relação aos benzodiazews lá?
Sim,
e aí
já
você
publiquei.
Até propôs o mecanismo lá. Na primeira etapa, na verdade, as beta-cyclodextrinas, elas não chegam a ativar o aldeído?
Sim, professor. Posso mostrar para você?
Por gentileza, eu não sei se vai dar para você mostrar agora.
Sim, só um pouquinho.
Só para a gente ver. Acho que é slide 36, né? Isso. Veja que aí você já tem a imina, né? A minha pergunta é, antes de formar a imina, qual seria o papel da cyclodextrina aí? Seria, na verdade, os hidrogênios ionizáveis seriam responsáveis pela complexação com oxigênio para deixar mais eletrofílica, carbonila?
Isso, professor, isso mesmo do ácidos Lewis. É porque aqui eu peguei direto imina, mas antes dessa etapa eu tenho que colocar aldeído com beta-cyclodestrin. Depois essa parte é a segunda escala.
Tá.
Entendeu?
Segunda etapa, no caso.
Isso, segunda etapa, isso.
Tá. Eu acabei imaginando, mas como vocês não representaram, poderia ser uma coisa meio óbvia, né? Porque ele vai funcionar, eu acho, como um ácido de Bronsted, né?
Sim.
Acho que seria isso, né?
Sim.
Daqui
isso.
a pouco a gente pode estar pensando em algumas outras reações aí pode falar no privado aí, depois, Ramesh, outras reações aí com essas cyclodextrinas, já que elas estão fazendo essa ativação da carbonila, né? Obviamente, vocês fizeram em especial a etapa aí de ciclização, né? Mas a gente pode, daqui um pouco, ver outras reações com relação a isso. Uma vez também que você falou que elas são economicamente viáveis, né? Então...
Essa é muito barata, professor. 1 quilograma, eu acho que na Índia é muito barato. 1 quilograma, porque nós usamos 10 mol por cento, né? Só pouco, mas 1 quilograma é muito barato. Eu acho que R$ 100 ou 150, só isso.
Ah, não, tranquilo. Então, bem barato.
Bem barato.
Bom, Ramesh, da minha parte, seria isso. Deixa eu dar uma olhada. A princípio, a gente não tem perguntas aí para fazer. Os alunos não têm dúvidas por enquanto. Se é assim, Ramesh, aqui no Brasil, quando não é prova, daí ninguém tem dúvida. Se fosse na véspera da prova, estava todo mundo tirando dúvida aí. Né? Então, é assim mesmo, tem que ir se acostumando aí com os alunos, tá? Brincadeiras à parte aí, pessoal, tá? Então, eu acho que podemos ir encerrando, tá? Parabenizo novamente a apresentação do professor Ramesh, e eu acho que ele deixou o contato, quem tiver interesse com ele, o professor Ramesh é bem acessível, a gente também está fazendo algumas colaborações já, né? Então, é só entrar em contato com ele, tá? Então, parabéns, professor, pelo seu trabalho aí, está bombando aí na FURG já. Tá, um agradecimento especial para quem presenciou a palestra também do professor Ramesh aí, tá? Então, desejo a todas aí uma boa semana, um bom resto de semana, um bom final de semana aí, tá? Fiquem todos bem, certo? Então, da minha parte, seria isso. Muito obrigado novamente.
Tá, obrigado, professor.